All right, guys, just so we can kind of see what we've covered in class today, just as a kind of review video, I want to go over kind of Hess's Law. First and foremost, remember we talked about enthalpy changes in class and understanding enthalpy in general. Remember, enthalpy is a extensive property, so it's going to be based off the amount that's present. We've already kind of talked about this, but notice kind of the first part here. We have nitrogen plus oxygen forming nitrogen dioxide, and we have a delta H of reaction that's 68 kilojoules. Remember, the positive means this is endothermic, meaning energy was taken into the system. Now notice the second reaction here is the same reaction, just the reverse. So now we have nitrogen dioxide splitting into nitrogen and oxygen. Notice what happens to our delta H. Instead of it being endothermic, it becomes exothermic, and it's still the same value. That's because, remember, this energy is based off the bonds that are breaking and that are forming. The bonds that are breaking in nitrogen and oxygen are the same bonds that are forming in the nitrogen and oxygen of the products here. Same with this guy. The bonds that are forming here are the same bonds that are breaking. So because it's the same bonds, it's just reversing who we're breaking and who we're forming, we end up with the same enthalpy value, just different charge, or different sign, I should say, not charge. And again, if the forward reaction is endothermic, the backwards reaction is exothermic. The same would be true if the forward was exo, the reverse would be endo. So pretty simple and pretty logical. Looking at the second step down here, or the second thing about enthalpy, we again have nitrogen and oxygen forming nitrogen dioxide. And notice our ratios here are 1, 2, and 2. And again, our delta H is still a positive 68, so again, still endothermic because we haven't flipped the reaction from how it was originally. Notice here, if I double my coefficient, so instead of 1, 2, 2, I have 2, 4, 4, notice what it does to my enthalpy. I double it. This goes back again to that extensive, and it's a 1-to-1 ratio. If I double my coefficients, I double the amount of bonds that I'm breaking and forming. Therefore, I double my delta H. Notice down here, if I half, because now I'm going from 1, 2, 2 to 1/2, 1, 1, I'm going to half my enthalpy. So it basically, whatever we do to our coefficients, remember we have to do to the whole reaction. So if I need nitrogen doubled, I have to double everything. Whatever I do to my reaction, I also do to my enthalpy. So if I triple my reaction, I have to triple my delta H. If I 1/4 or 1/4 my reaction, I have to do the same thing to my delta H. So just kind of in recap, if we flip the reaction, we flip the sign of the delta H. If I change the magnitude of the coefficients, I change the magnitude of delta H. So pretty simple. Now let's look at why we use this. We use this in Hess's Law. Hess's Law is basically going to be used in both delta H, which we're doing enthalpy, delta S, entropy, and delta G, Gibbs free energy. So it's a law that applies to all thermodynamics in terms of the calculations we're going to use. So thankfully, once we get Hess's Law with enthalpy, we'll get it with entropy and Gibbs free energy as well. What it basically says is that if I have A and B that I'm starting with as my reactants, and I'm going to C and D as my products, the enthalpy for that reaction is going to be the same regardless of if it happens in one step or multiple steps. So we can kind of see that down here. Okay, nitrogen plus oxygen forming nitrogen dioxide. Again, same reaction we've been working with. Has a 68 kilojoule enthalpy. Notice here, let's say instead nitrogen plus 1 oxygen produces 2 nitrogen monoxides, and those 2 nitrogen monoxides plus oxygen produce 2 nitrogen dioxides. If we go through and look at the overall process, so let's say this is step 1 and this is step 2, the reaction does match our overall reaction up here. So notice our 2 nitrogen monoxides would cancel on both sides. We would have 1 nitrogen coming down plus 2 oxygens going to 2 NO2. So it matches our original reaction. And what we would do with our delta H is add them together. So in this case, 180 plus negative 112, we get 68 kilojoules. So this is kind of Hess's Law. And this is why knowing that our reactions and how they relate to enthalpy is important. So let's say we had to flip this second step. we would have flipped the sign for our delta H for that second step. Let's say we had to double our second step. We would double our delta H here as well. So let's kind of look at an example and kind of see how this works. Okay, so we're looking at graphite and diamond, same two people we talked about when we were doing our solids and types of solids with network solids early on. We want to know, based off the enthalpies of the reaction, so we have the combustion of graphite is negative 394 and the combustion of diamond is negative 396. I want to know what the delta H is going to be for going from graphite to diamond. Okay, well, I can use these two reactions and Hess's law to figure out what one reaction is going to be, because whether it happens in 2 steps or 1 step, it's going to be the same delta H. So with that being said, I want to start with graphite, I want to end with diamond. So I want graphite to be on my reactant side. So I'm going to leave this reaction just the way it is. So I'm going to rewrite it down here. So C graphite plus oxygen produces CO2, and that delta H is going to stay exactly as negative 394. Okay, but notice the second reaction. Oops, sorry. Stop it. Notice the second reaction. The second reaction has diamond also as a reactant. I don't want it as a reactant, I want it as a product. So I'm actually going to flip that reaction. So CO2 plus, oops, sorry, let's do diamond first. Diamond plus O2. And remember what that does to our delta H is it's going to change the sign. So instead of 396, negative 396, we're going to get 396, positive. Okay, now what we can do is double check that we've set this up correctly by canceling it down and making sure we get the reaction we're supposed to get. So CO2 cancels out and O2 cancels out. So graphite to diamond. And if we look, that's the reaction, exactly what we're looking for. And now we can add up our delta H's and get our actual number. So negative 394 plus positive 396 gives us a positive 2 kilojoule for this process. Okay, so not too bad. Let's look at another one. Let's say I have this as my goal reaction. I want to know the delta H for this reaction. Well, I don't have that reaction. I have these different steps that can make that reaction. And I want to know what the delta H is. Well, I have these delta H's that I can use to calculate the overall delta H here. Because remember, Hess's law says regardless of if it happens this way or this way, it's going to be the same delta H. So let's kind of walk through this and see how this ends up working. Okay, so I'm going to look at my first step, and I always take it 1 step at a time. You might be able to put them all together and go from there, but I feel like that's a little overwhelming. So let's just take 1 step at a time. We have 2 borons, 3 half oxygens forming B2O3. Well, if I look up here, I'm going to see if anything matches in this first reaction, because remember, this is my goal. I'm trying to make this reaction using these reactions. Well, I see my 2 borons here, and the other 2 guys aren't in there, so that tells us we'll deal with them a little bit later. But the 2 borons I want in my overall reaction. And notice they're on the same side as the arrow. 2B is our reactant, and it's a reactant here. So I'm going to leave that reaction alone, and I'm just going to rewrite it down here exactly the way it is. Okay? And I'm going to write the delta H over here. I didn't change anything about the reaction, so I'm not changing anything about my delta H. It stays exactly the way it is. Now on B, notice I have this B2H6. Well, that's the product I want, but it's not a product here. It's also in the same number I want, so I want 1 B2H6, 1 B2H6 here. So because I want this on the product side, I'm going to flip this reaction. So B2O3 plus 3H2O going to B2H6 plus 3O2. And that's now going to be a delta H of 2035 because it's now positive. Okay, so now we add these 2 reactions and our delta H's together. So B2O3 is on both sides and oxygen's on the both sides. So there's 1.5 oxygens here and 3 here. So the 1.5 is going to go away and 3 is going to become 1.5. So 3 seconds again. So now I can rewrite this, and I'll kind of do like what you would do in elementary math and just kind of equal it down like you would a simple math problem. So 2 borons plus 3 waters. And something to make note is this water here is a gas. So I'm going to put the state of matter just for this guy, because it does end up being important in a little bit. B2H6 and 3 half oxygens. And we'll add up our delta H's. And what we get here, negative 1,273 plus 2,035, gives us a delta H of positive 762. Okay, well, I'm going to scroll up just a little bit and keep our B and C in range. Okay, remember I mentioned that this is a gaseous water. Well, if I go up to my actual original reaction, there's no water in here, so I know I have to get rid of that water. But I also know I need to get hydrogen in this reaction. So I do have this hydrogen here, so we kind of have 2 options. We can start with C and just know we have 2 waters to take care of, or just go ahead and get rid of the gaseous water, get it into liquid water, so that we can get rid of this liquid water eventually. It's up to you which one you start with. Let's maybe just keep it somewhat simple and go ahead and start with this guy, just because it's the next one in line. Okay, so notice here, actually let's go back up and look at our reaction. Hydrogen is on the reactant side, so I want to keep it on the reactant side, but there's 3 of them, so I need 3 of them. So what I'm going to do here is I'm going to triple that reaction. And notice this is liquid water, which I can't do anything with just yet. And that gives me a delta H of negative 858. Okay, so now we're going to go through, cancel out, and add up our new delta H. So we have 3 half oxygens on both sides. It will go away. I cannot cancel out my waters because they are different states and matter, so that does play a role here. So now I'm going to rewrite it as 2 borons plus 3 hydrogens plus 3 H2O gas going into B2H6 plus 3 H2O liquids. Okay, and then calculate our delta H again. Okay, and that's going to give us a negative 96. And again, just going to do a line right here because that represents kind of our, we've done these 2, added them up and got this guy, added our next guy and got that guy. Okay, so now we have our last reaction. And again, if we go back up to our original, water's not in that reaction, so we now have to get rid of it. We'll get rid of it with this guy. So notice gaseous water is on the reactant side. So I want to keep it on the product side here so I can cancel it out. So this guy is already set up the way we want it. The problem are the coefficients. I have 3 waters, 3 waters. So I'm going to triple that reaction and make it 3 H2O liquids going to 3 H2O gases. And that's going to give us a delta H of positive 132, since we didn't switch that the reaction around at all. So we cancel out what we can, 3 waters, 3 waters, 3 waters, 3 waters, and we're left with 2 borons plus 3 hydrogens forming B2H6, and this guy is going to have a delta H of 36 kilojoules. So double check, 2 borons plus 3 hydrogens equals B2H6. 2 borons plus 3 hydrogen equals B2H6. So my original question is, what is the delta H for this guy? Well, the delta H is going to be 36 kilojoules.